On the horizon, the sky begins to darken. The air thickens, heavy, almost sticky with moisture. From afar comes a low, trembling rumble, as if the earth itself were warning of what's about to unfold. The wind shifts. The scent in the air changes, metallic, sharp, electric. Moments later, over the flatlands of the American South, a force is born that nothing can stop. From an otherwise calm sky, a narrow spiral descends, hesitant at first, then swelling, twisting, devouring everything in its path. That's how a tornado begins, thousands of kilometers away, above the warm waters of the Atlantic. Another kind of monster gathers strength. Swirls of air and vapor rise, forming a massive cyclonic engine that moves slowly, deliberately across the ocean. At first it seems distant, harmless even, but hour by hour it grows. The wind accelerates to hundreds of kilometers per hour. Waves climb to the height of buildings, and clouds form a perfectly symmetrical eye, the calm center encircled by a ring of devastation. Tornadoes and hurricanes. Two faces of the same raw force. Different in scale, identical in purpose. One is sudden, striking without warning, vanishing in minutes but leaving behind splinters and silence. The other approaches slowly, like a shadow that stretches over days, giving time to prepare, but never enough to escape fear. They remind us of our fragility. They strip away the illusion of control and show again and again that no matter how advanced our technology or how precise our forecasts, we remain guests on a planet ruled by the laws of nature. For those who live in their path, these are not just meteorological terms. They are sensations. The scream of the wind tearing through the night, flashes of lightning splitting the sky, the metallic scent of ozone, and then silence. The kind of silence that feels wrong, the silence before destruction. But these stories are also about survival, about people who've learned to listen to the sky, to read the language of clouds, to recognize the pulse of the wind. Communities that rebuild again and again, who sift through rubble, plant new trees, and return to life. Because in every storm, no matter how violent, there's a lesson that life on Earth is a constant dialogue between humankind and the elements. Then comes that moment before everything breaks, when the world seems to hold its breath. The air stills. On the horizon, the boundary between sky and land quivers. You can feel it before you see it. A pulse, a hum, a vibration growing stronger by the second. A tornado isn't born of chaos, it's born of precision. Of mathematics written in air, of balance pushed just far enough to awaken fury. At first it's only a meeting. Warm, moist air from the Gulf colliding with a cold front from the north. But when that meeting happens at exactly the right moment, in exactly the right place, something greater is born, a vertical current of air that begins to spin faster and faster until the sky releases a narrow, dark funnel, a column of pure energy, the tornado. It is one of Earth's most complex and brief phenomena. It may last only minutes, sometimes half an hour, yet its power can erase entire towns. Inside the funnel, winds can exceed 500 kilometers per hour. The pressure difference between its core and surroundings is so immense that it can lift asphalt from roads, toss cars like leaves, and splinter houses into dust. Tornadoes are both physics and poetry, born of balance and disturbance, of stillness and motion. To the human eye, they seem wild and random, but in truth, they are the perfect choreography of billions of air molecules moving in unison. A spiral that forms in silence, matures in chaos, and disappears into emptiness. Most often, they arise in the fabled Tornado Alley, the vast corridor stretching through Texas, Oklahoma, Kansas, and the Dakotas. Geography, ocean currents, and continental winds converge here to create the perfect stage for destruction. Each year, this sky becomes a theater where nature performs its most powerful act, reminding us that technology offers not control, but only the illusion of safety. No two tornadoes are alike. Some are slender threads dancing harmlessly across open fields. Others are monstrous cones blotting out the horizon. Black, swirling masses of dust, lightning, and debris. Inside, there is no silence. Only a deafening roar, like a freight train charging through the air itself. There is no light, no dark, only a churning gray where earth, wood, metal, and life itself spin together. Scientists have tried for decades to understand them. We know that tornadoes are born within supercells, massive storm systems where rising air begins to rotate, forming mesocyclones, the atmospheric engines that can reach down and touch the ground. But even with satellites, Doppler radar, and powerful simulations, the precise moment of birth remains a mystery. What a meteorologist sees as a pattern in the clouds, a farmer on the plains sees as the end of the world. And perhaps the strangest thing, tornadoes can be selective. One house obliterated, the next untouched. A tree stripped bare, yet a single flower still stands. It's not magic, it's chaos embodied. Every breath of wind, every swirl of pressure determines the fate of a place, a life, a moment. Yet for all their violence, there's a kind of terrible beauty in them. From a distance, from safety, a tornado is mesmerizing. A column of shadow and light, stitching earth to sky, a reminder of the fragile thread that binds what is human to what is elemental. And when it's over, there's the quiet, the kind that hums in your ears because there's nothing left to hear. The drip of water from a broken roof, the creak of twisted steel, the faint song of a bird that somehow survived. That's when the world exhales, when people step outside, see the ruin, and begin again. Because even after the wind has stripped everything bare, something in us still insists on rebuilding. Every tornado leaves a mark, not only on the landscape, but also in memory. For the people of Oklahoma, Kansas, and Arkansas, it's more than just a natural disaster. It's part of who they are. They learn to live with it, to read the sky, to know when to take shelter, and when to look up with quiet respect. Children in schools are taught how to respond to warning sirens, while adults can tell what kind of cloud they're looking at with a single glance. It's a modern dance with nature, not a fight, but an act of acceptance. In a way, a tornado is also a metaphor for human life. Suddenly, without warning, it can change everything, shatter, destroy, upend. But after every storm comes silence, and after destruction, rebirth. A tornado reminds us that strength and fragility are inseparable, that life is both fragile and resilient, and that even in the heart of chaos, there is an order that humanity is only beginning to understand. The sky over the plains has its own language. To an outsider, the storm clouds may look like a bad omen, heavy, leaden, hanging low over the horizon. But to those raised in Oklahoma, Kansas, or Nebraska, it's the daily alphabet of life. They know that not every cloud means destruction, but also that sometimes a single gust of wind, one uneasy swirl in the air, can be the beginning of something that changes everything. A tornado isn't just a meteorological event. It's part of culture, identity, and generational memory. In many towns across America's heartland, every child knows where the nearest shelter is, what the siren sounds like, and how many seconds they have once the first tone hits the air. In basements and classrooms, they practice regularly, not out of fear, but out of respect for nature. For these people, tornadoes are no longer an unknown monster from the sky, but something more personal. A neighbor that can't be ignored, but must be lived with. Some say they can feel the change in the air before the radar even confirms it. The sky gets heavier, they say. It's like the earth is holding its breath. Many who have survived a tornado say the experience changes everything. When a home disappears in seconds, when trees are torn out by the roots, when the air itself becomes a carrier of chaos, a person loses the illusion of control over the world. But in that very moment, something else is born. Deep humility toward life itself. After a tornado passes, the landscape looks like another planet. Power lines lie across the ground, roofs vanish, and crops that swayed in the morning wind are pressed flat as if by an invisible hand. And yet among the ruins, people always appear. They help each other, rescue animals, bring water, and search for family mementos in the debris. A tornado can destroy a house, but it often awakens something that was missing before. Solidarity. Some believe those experiences remain in the soil, That places touched by tornadoes carry a unique energy, a mixture of pain, relief, and new beginnings. When trees grow back, when new houses rise, there's still something invisible in the air. The memory of that wind. Psychologists say that the trauma of surviving a tornado is unique, not only because it's sudden and destructive, but because it strips people of their sense of control. A person who spent a lifetime building a home, a garden, a farm, loses it all in minutes, and there's no one to blame. You can't accuse anyone. You can't predict it. You can't stop it. Yet, in that powerlessness lies something essential to human nature: the ability to rebuild. After every tornado season, communities rebuild. New towns, new schools, new bridges rise from the ground. People return to the places where they lost everything. Not because they've forgotten, but because they understand that life is a cycle: storm, silence, renewal. For meteorologists, a tornado is a system of pressure gradients and Coriolis forces. For the people who live beneath it, it's the voice of nature, one that must be heard and respected. In movies and news reports, it's often described as a monster, but those who truly live under its sky tell a different story. They say a tornado is like the Earth's breath, sometimes violent, sometimes gentle, but always real. In a sense, tornadoes teach humility, something that's often missing in the age of technology. They show that despite satellites, sensors, and artificial intelligence, there are still forces we cannot master. That in a world of data and predictability, nature still holds the element of surprise. But they teach something else too. Survival is not about fighting, it's about adapting. Modern homes in Tornado Alley are built with the wind in mind. Schools have underground shelters, and farmers watch the sky with the same reverence their ancestors once reserved for the land. The tornado becomes part of life's rhythm, a reminder that humanity is not above nature, but within it. Over time, people also learn another lesson: beauty and terror can coexist. Seen from a safe distance, a tornado can be almost mystical, a dance of light, shadow, and lightning moving across the horizon. For many photographers and storm chasers, it's a moment of transcendence, when understanding and fear intertwine. But even they know that such fascination comes with a price. Because when nature reveals its power, all one can do is watch, in awe and humility. And in the end, after every storm, comes stillness. The air smells of ozone, and mist rises above the fields. In the fading light of sunset, you can see a single tree still standing where everything else has fallen. Its roots cling to the earth, its trunk is scarred, but it's alive. And that tree, like the people, becomes a symbol of survival. Every tornado begins in silence, not an ordinary calm, but a tension, as if the air itself knows that something unstoppable is about to happen. Clouds gather on the horizon, the air grows heavier, and the wind starts to spin in invisible spirals. It's the moment when worlds collide. Warm, moist air from the south meets cold, dry air from the north. And from that clash, something is born that has neither beginning nor end. Motion that turns chaos into a vortex. A tornado is the child of a supercell, the most complex and powerful storm system the atmosphere can create. At its heart lies a mesocyclone, a giant rotating column of air within the thundercloud. That's where the future monster forms, invisible to the human eye, but already aware of its strength. Rising and sinking air currents spin in the same place, creating a vertical column that gathers more and more rotational energy. Rotation is the key. Air drawn upward from the surface begins to spin around an axis, and the contrast in temperature and humidity intensifies the motion. At a certain point, the energy that had been scattered across the clouds concentrates in one place. Then, from the base of the storm, a condensation funnel descends. At first, thin and translucent, then darker, until it finally touches the ground. At that moment, a tornado is born, but its life is brief. Most tornadoes last only a few minutes, some mere seconds. Only the rarest and strongest can travel for dozens of miles, destroying everything in their path. Each tornado is different. It has its own shape, rhythm, and movement. Some are slim and graceful. Others are massive cones or walls of dust that move like living mountains. The inside of a tornado is both a physical and symbolic boundary between the known and the unknown. The pressure within the vortex drops sharply, sometimes by dozens of millibars, sucking the surrounding air inward. Winds can reach over 250 miles per hour, and the flow isn't uniform. Every layer, every meter of air spins at a different speed and angle. That's what makes a tornado so unpredictable. From a scientific standpoint, a tornado is the ultimate expression of balance and its collapse. Nature abhors stagnation. Where energy accumulates, it must be released. A tornado is the atmosphere's way of resetting tension. But within that process lies something more than physics. Something almost alive, as if the storm itself possessed awareness. As the tornado moves, its shape and structure constantly change. Sometimes it splits into smaller vortices, satellite tornadoes, that dance around the main funnel like planets orbiting a sun. Occasionally, it shifts direction as if choosing its own path. To an observer, it's pure chaos. To the atmosphere, it's perfect balance. In the very center of the vortex lies silence. That paradox fascinates both scientists and poets. Inside the so-called eye of the storm, air movement is surprisingly calm. It's the heart of the tempest. Not beating, just suspended. While destruction rages all around, that stillness reveals something profound about chaos. That even in the wildest turmoil, there's a point of equilibrium. When a tornado loses its energy, when cooler air floods in, when updrafts weaken, when the parent storm fades, the vortex collapses. It vanishes as suddenly as it appeared, leaving behind silence, dust, and the scent of wet earth. Scientifically, the process is over. In human memory, it remains a dark column cutting through the sky like a mark. Studying tornadoes remains one of meteorology's greatest challenges. Their short lifespans, unpredictability, and immense power make it nearly impossible for any technology to fully capture what happens inside. Satellites, radars, drones, they all offer only fragments. That's why scientists and storm chasers still pursue them, chasing not just data, but mystery. A tornado is like the Earth's breath, violent, terrifying, yet necessary. Through it, the atmosphere releases energy, redistributes moisture, and restores balance. What is catastrophe for humans is, for nature, an act of healing. In a way, a tornado mirrors life itself, born of tension, growing through chaos, reaching peak strength, then fading, leaving behind traces, not only on the land, but in the minds of those who witnessed it. Watching its birth and death teaches humility before a world that, despite all our science and technology, remains wild and unpredictable. Though a tornado is the atmosphere's most violent display of force, its reach and lifespan are limited. The vortex that can wipe out a town in minutes is only a spark compared to what happens over tropical oceans. There, where the water temperature rises above 80 degrees and the air is heavy with moisture, a planetary power awakens. The hurricane. It's not a single funnel, but a massive, self-sustaining system capable of traveling thousands of miles, feeding directly on the ocean's warmth. If a tornado is a spark, a hurricane is a fire, one fueled by endless evaporating water. The birth of a hurricane begins with something small, instability in the atmosphere. Warm, moist air over the ocean rises, creating a zone of low pressure near the surface. Cooler air rushes in to replace it, warms and rises in turn, setting off a circulation. As the water vapor ascends, it condenses, releasing immense amounts of latent heat, further warming the air and accelerating its upward motion. This is the key. A hurricane is essentially a giant heat engine that converts solar energy stored in the ocean into atmospheric motion. Gradually, structure emerges from chaos. A tropical disturbance evolves into a tropical depression, then into a tropical storm. This is when the system begins to organize. Heat, moisture, and planetary rotation start to cooperate. The critical factor is the Coriolis force, caused by Earth's rotation, which sets the air into a spin. In the northern hemisphere, hurricanes rotate counterclockwise. In the southern, clockwise. Without this force, hurricanes wouldn't form at all, which is why none appear near the equator, where the Coriolis effect is too weak. Once the system reaches critical scale, self-amplification begins. The more warm air rises, the lower the central pressure becomes, drawing in even more air from the surroundings. Wind speeds grow exponentially. At several miles up, condensed vapor forms dense cloud bands that spiral around a central point, the eye of the cyclone. Inside it, paradoxically, there is calm. The temperature is higher, and the sky may even be clear. While around it, in the eye wall, winds exceed 120 mph and rain falls with unimaginable intensity. It's the storm's most dangerous zone, where oceanic and atmospheric power collide. The energy a hurricane extracts from the ocean is staggering. In a single day, a typical hurricane releases as much heat energy as hundreds of thousands of nuclear bombs. Yet despite its power, the process is entirely natural, precise, almost mechanical. The feedback loop is the key. The more heat the ocean transfers to the air, the stronger the vortex becomes, which in turn increases evaporation. As long as the storm remains over warm tropical waters, it strengthens. Once it moves over cooler seas or land, it weakens, its energy source cut off, the cycle broken. Ultimately, a hurricane is a mechanism of balance, a way the planet redistributes heat from the tropics toward higher latitudes. Without these tropical storms, Earth's climate would be far more unstable, with oceans storing dangerous excess heat. Though a hurricane is a human catastrophe, for the planet it's equilibrium, a release of tension between ocean and sky. At the moment of its birth, somewhere above a warm sea. There's no drama, just a quiet, logical process. Only later does it grow into a monster capable of destroying cities. Yet its essence never changes. Sunlight, water, planetary rotation, and the laws of physics. 4 elements that, under perfect conditions, create the most powerful weather system our planet knows. A hurricane isn't a random swirl of clouds or air. It's a precise, self-regulating system like a living organism with a heart, lungs, bloodstream, and nerves. Its anatomy is a work of physics, but in its complexity, it feels almost biological. To understand a hurricane is to take apart one of nature's grandest machines, one that unites wind, water, and heat into one of the most awe-inspiring phenomena on Earth. At the very center of a hurricane lies the eye, a place of apparent calm and paradox. Measuring anywhere from 20 to 50 kilometers across, it seems peaceful, even serene. Though just beyond its borders, rage winds powerful enough to tear apart steel structures. Within the eye, the pressure is the lowest in the entire system, and instead of rising, the air slowly sinks toward the surface of the ocean. As it descends, it warms adiabatically, often clearing the sky and allowing sunlight to pierce through the surrounding clouds, creating the illusion of tranquility. In reality, it is the heart of destruction. When the eye passes over land, everything caught within its wall is leveled to the ground. The eye wall, the boundary between silence and chaos, is a ring of the most intense atmospheric phenomena on Earth. Here, air rises at hundreds of kilometers per hour, carrying enormous amounts of water vapor that condense and release latent heat. It is this heat that powers the entire system. The eye wall is dynamic, constantly changing shape and structure, expanding, contracting, and sometimes forming concentric rings in a process known as the eye wall replacement cycle. During this phase, the inner wall weakens while a new outer wall intensifies, causing a temporary weakening of the storm before it often re-strengthens. Beyond the eye wall stretch the spiral rain bands, vast systems of thunderclouds that extend hundreds of kilometers from the center. These bands bring torrential rainfall and violent gusts of wind, creating the iconic spiral pattern seen in satellite imagery. Each band acts as a miniature convective system, where warm, moist air rises and cools, producing rain, then sinks again, to fuel the cycle anew. Within these rain bands, smaller phenomena emerge, tornadoes, squalls, and abrupt pressure drops, smaller storms within the greater one. On the outermost edges of a hurricane lie zones that may appear calm, yet they form the storm's foundation. From hundreds of kilometers away, air is drawn inward by pressure differences. As it approaches the center, it accelerates and begins to curve, a result of the Coriolis effect, which gives the hurricane its spiraling motion. Viewed from the side, a hurricane resembles an immense heat chimney. Warm air ascends through the eye wall, while cooler air sinks within the eye and along the periphery, completing the circulation. It is a closed system, sustained as long as it can draw heat from the ocean, maintaining balance for days at a time. At altitudes of 10 to 15 kilometers in the upper troposphere, the hurricane spreads its wings. The air that rises in the eye wall fans outward, radiating across the sky and creating a shape reminiscent of a blossoming flower. In this layer, thin cirrus clouds form, delicate feather-like wisps that can herald the storm's approach hundreds of miles before landfall. At this level, the hurricane releases its excess heat into space, closing its energy cycle. What makes a hurricane so stable and long-lived is the delicate equilibrium among heat, moisture, and motion. If any one of these factors is disturbed by cooler waters, a dry air mass, or land interaction, the system begins to decay. The energy supply is cut off, circulation weakens, and the structure collapses. Despite its appearance of invincibility, a hurricane is in truth an extraordinarily fragile creation, the product of nearly perfect conditions that can persist only briefly in Earth's atmospheric history. From a scientific standpoint, a hurricane is a planetary-scale physics laboratory. Within a single storm converge the processes of convection, evaporation, condensation, fluid dynamics, and thermodynamics. Each can be described by equations, but together they form something no simulation can fully capture: a self-organizing, dynamic system that behaves almost like a living organism, capable of adapting and responding to its environment. And yet, despite this scientific precision, there is something almost metaphysical about a hurricane. At its center, literally and symbolically, lies calm within chaos. The eye of the storm is like the heart of nature itself, beating slowly while everything around it whirls in unrestrained fury. It is a place glimpsed by pilots and satellites, but whose power cannot be fully expressed in words. There, in the silence, one becomes aware that we live on a planet where every force, even the most destructive, is part of a greater order. Balance and beauty. A hurricane is born of heat, sustained by the ocean, and dies when that heat is taken away. Its life cycle is not merely the story of a single storm, but a narrative of energy, balance, and inevitable impermanence, as if nature were creating colossal organisms that are born, mature, and perish in rhythm with the planet itself. It all begins innocently, with a tropical disturbance, a small cluster of thunderclouds over a warm sea. The ocean surface must reach at least 26.5 dectagas, about 80 degrees, and the upper atmosphere must cool rapidly with height. The steeper the gradient, the easier the air rises. From these hot, moist air masses, vertical convective currents form and start to spin under the influence of the Coriolis effect, the consequence of Earth's rotation. At that moment, the embryo of a cyclone is born. As the vortex gains strength, its structure organizes. Air from the surroundings flows inward, rising in a spiraling motion through the atmosphere. Water vapor condenses, releasing vast amounts of latent heat, the hurricane's fuel. This process, repeated billions of times every second, powers the storm's heart. Each droplet that transitions from gas to liquid transfers energy to the surrounding air, heating it and driving it upward even faster. Over time, the system begins to feed on itself. Winds that were once erratic and weak find rhythm and structure. When sustained winds reach 74 miles per hour, the tropical cyclone is officially classified as a hurricane. From that point on, its existence becomes a battle for equilibrium between centrifugal force, which threatens to tear it apart, and pressure gradients, which hold it together. It's a balance so delicate that a minor change in sea temperature or moisture inflow can determine its fate. Hurricanes have distinct personalities. Some are short-lived and weak, fading after a few days before ever touching land. Others, like Katrina, Irma, or Patricia, grow into colossal beasts, maintaining perfect equilibrium for days, fueled by the constant warmth of the ocean. Their trajectories are the result of a complex interplay of air currents, trade winds, highs, lows, and jet streams that can steer a storm hundreds of miles in one direction or another. But no hurricane is eternal. When its core moves over cooler waters, its evaporative energy supply dwindles. Winds lose intensity, the structure unravels, and clouds disperse into broad sheets of rain. Sometimes death comes suddenly, when a hurricane strikes land, cutting itself off from its heat source. Denser air, surface friction, and dry continental masses disrupt its symmetry. The eye collapses, the eye wall disintegrates, and within hours the massive system can dissolve into an ordinary low-pressure area. Yet not all endings are final. Part of a hurricane's energy can survive in another form. As its remnants move into cooler regions, the system can transform into what's known as an extratropical cyclone, a frontal storm powered not by oceanic heat, but by the contrast between warm and cold air. These reborn hurricanes can still wreak havoc, no longer with tropical fury, but through powerful winds and torrential rains. The life of a hurricane is, in essence, the story of energy in motion. Heat transferred from the ocean to the atmosphere, and from the atmosphere back into space. In this sense, every hurricane is part of Earth's global energy circulation, essential to the planet's climate balance. Though catastrophic for humanity, hurricanes play a vital planetary role, redistributing heat from the tropics toward higher latitudes, tempering temperature extremes that would otherwise be far more severe. Nature knows neither good nor evil, only balance. A hurricane, though destructive, is one of the mechanisms of that balance. It reminds us that nature's power does not arise from chaos, but from harmony between forces that humans often perceive as opposites. Heat and cold, evaporation and condensation, life and death, all parts of a single, ongoing cycle. And when a hurricane finally dissipates, its echo remains in the atmosphere, in cooler waters, in rainfall thousands of miles away, in air currents that carry its energy for weeks. It is not an ending but a transformation. The energy that gave birth to the storm does not vanish. It returns to the ocean, the clouds, the sky. And there, in the quiet of the tropics, as the water warms once more, a new vortex begins to form. Slowly, invisibly. A hurricane is not merely a physical phenomenon. Its presence in the human psyche acts as a powerful catalyst for emotion, blending fascination, fear, and awe before forces that cannot be controlled. The mere sight of darkening skies above the ocean, rising waves, and winds awakening from stillness triggers primal reactions. Tightened muscles, racing hearts, and the instinct for survival. Reminders of how fragile human life is in the face of nature's might. The psychology of hurricanes is shaped by complex cognitive processes. For centuries, people have tried to predict their paths, to forecast, to mitigate their impact. Yet despite satellites and supercomputers, an element of uncertainty always remains. That unpredictability is what draws scientists, meteorologists, and ordinary observers alike, a magnetic pull between risk and understanding. The eye of a hurricane, calm and symmetrically perfect, evokes a paradoxical sense of safety in the midst of chaos. A suspended moment in time when one can feel both relief and an existential connection to nature's immense power. In the human mind, a hurricane often becomes a metaphor for life's inevitable forces: change, loss, unpredictability. Fear of the storm intertwines with admiration for its beauty. Swirling air, lightning splitting the sky, the roar of wind and crashing waves form an aesthetic, almost mystical experience that transcends simple fear. Some describe it as a kind of storm hypnosis, a state where adrenaline merges with awe, and the mind becomes wholly absorbed in watching the movement of clouds, shifting light, and the rhythm of the wind. Psychologists also emphasize the social dimension of hurricanes. Anticipation, evacuation, and preparation mobilize communities, while fear of the unknown strengthens social bonds. People share information, organize aid, and perform rituals of readiness, from boarding up windows to stockpiling supplies. In this way, a hurricane becomes a catalyst for cooperation, solidarity, and care. On a personal level, hurricanes act as mirrors of the human psyche. People are drawn to their terror and beauty alike, following radar maps, watching through windows, or even flying above the storm. Emotional resonance with such events can lead to catharsis, a cleansing through confrontation with something greater than oneself, or to existential anxiety, a reminder of life's fragility. Symbolically, hurricanes represent forces of change beyond our control, much like those that shape our lives. People project their own experiences onto them: loss, transformation, renewal. The storm that destroys landscapes also purifies the air, brings rain, and revives ecosystems, making the hurricane, in the human imagination, a metaphor for renewal and the eternal cycle of life. Finally, our fascination with hurricanes has found its place in culture, literature, and art. Filmmakers, writers, and artists strive to capture their power, while scientists dissect every element, from wind dynamics to pressure shifts. It shows that the psychology of hurricanes extends beyond fear or reverence. It encompasses humanity's creative and intellectual engagement with forces that both terrify and inspire. Hurricanes, or tropical cyclones, have always been integral to Earth's dynamic climate system, though their nature and intensity have changed dramatically across geological time. Modern satellites allow us to study them in real time. But to grasp how powerful ancient hurricanes once were, we must turn to the planet's natural archives: rocks, marine sediments, ice cores, and tree rings. These records reveal that some prehistoric storms may have surpassed anything we have witnessed in modern history. As far back as the Pleistocene epoch, roughly 2.6 million to 11,700 years ago, hurricanes may have reached intensities almost unimaginable today. Analyses of marine and deltaic sediments show distinct layers of sand and debris indicative of massive tropical storms. These storm deposit layers allow scientists to reconstruct the frequency and strength of ancient hurricanes. At the time, ocean surface temperatures were thermally uneven, and ocean currents differed from today's patterns, conditions that likely fostered the formation of immense tropical cyclones. Warmer sea surfaces encouraged rapid intensification, while sharper thermal contrast between ocean and atmosphere generated storms with staggering kinetic energy. Throughout the Holocene, the epoch stretching from the end of the last ice age to the present, evidence suggests that the planet once faced hurricanes far mightier than any recorded in modern times. Marine sediment cores taken from the Gulf of Mexico and the Caribbean reveal microscopic shells and fragments of marine organisms displaced by colossal storm surges. By examining these layers, scientists can reconstruct the intensity of ancient tempests, many equivalent to Category 5 hurricanes on today's Saffir-Simpson scale, and some perhaps even stronger. Periods of warmer oceans in those distant millennia likely fueled storms spanning more than 300 miles across, with wind gusts exceeding 200 miles per hour. On a geological timescale, hurricanes have acted not merely as atmospheric events, but as sculptors of the planet's surface. These immense tropical storms shaped coastlines, redirected river deltas, and transported sand and rock across vast distances, leaving behind landscapes still marked by their passage. Tree ring studies from coastal zones show that some trees growing in the hurricane belts of the Holocene bear the scars of repeated tempests: twisted trunks, alternating thick and thin growth rings, and sudden pauses in development. All silent witnesses to centuries of violent storms that devastated vegetation and forced ecosystems to begin anew. Natural climate cycles have long influenced the rhythm and power of these storms. Phenomena like El Niño and La Niña, along with variations in solar activity and the global conveyor of ocean currents known as thermohaline circulation, shaped the frequency and strength of hurricanes in the past. Around 6,000 years ago, during the mid-Holocene, the Atlantic Ocean was warmer than it is today, likely encouraging both more frequent and more intense hurricanes. Patterns also shifted with latitude. While the North Atlantic saw powerful storms, other regions experienced milder, more moderate cyclones. Geological records indicate that ancient hurricanes may have lasted longer and moved more slowly than those of the modern era, traits that greatly amplified their destructive potential. Lingering storms dumped torrential rainfall, triggering widespread flooding, while their massive size generated storm surges capable of remaking entire shorelines. Compared with even today's most violent super hurricanes, many ancient tropical cyclones combined ferocious wind speeds, overwhelming rainfall, and vast diameters to create forces of nature almost beyond imagination. Paleoclimate. Research also points to intermittent periods of so-called hyper-hurricanes, epochs when both the power and frequency of tropical cyclones far exceeded anything seen today. These extraordinary events were likely tied to global warming episodes within the Holocene or even earlier in the Pleistocene, when ocean temperatures ran significantly higher. The record makes clear that hurricanes are not only weather phenomena, but long-term geological agents, forces that have, for millions of years, shaped Earth's climate, landscapes, and living systems. By tracing their ancient history, scientists gain not just foresight into future storms, but a deeper understanding of the complex interplay among oceans, atmosphere, and life itself. Understanding how hurricanes evolved from deep geological time to the modern era also helps explain why today's storms rarely reach the cataclysmic proportions of their prehistoric predecessors. One crucial factor is the relative cooling of ocean waters in hurricane-forming regions since the warm phases of the Pleistocene and early Holocene. Back then, higher sea surface temperatures in the Atlantic and Pacific fed immense low-pressure systems that could build strength for days, accumulating staggering reserves of kinetic and thermal energy. Today, though oceans remain the great engine of storms, shifting currents and cooler conditions limit both the growth rate and maximum diameter of tropical cyclones. Atmospheric structure has changed as well. Ancient hyper-hurricanes developed in a calmer upper troposphere, with less wind shear and lower salinity in the surrounding air, conditions that allowed storms to mature undisturbed for extended periods. Modern skies, in contrast, are shaped by stronger jet streams that disrupt storm organization, tear at their central cores, and fragment their spiral rain bands before they can reach full strength. The depth of the ocean's thermocline, the warm layer that feeds hurricanes, has also proven decisive. In earlier epochs, tropical waters were not only warmer but thermally deeper, providing vast reserves of energy for cyclonic growth. Today, although surface waters can still be hot, the warm layer is relatively shallow, forcing storms to exhaust their energy supply more quickly and limiting their expansion. Land masses now play a greater role too. During the Pleistocene and early Holocene, many areas that are continents today were still submerged or existed as shallow marine basins, offering hurricanes uninterrupted expanses of warm water. Now, islands, peninsulas, and continents disrupt storm structure, shorten their lifespans, and reduce the energy they can draw from the sea. Even Earth's living systems exert influence. Forests, coral reefs, and coastal ecosystems act as natural buffers, scattering a storm's energy and locally dampening its impact. Though their effect is small in global terms, they remind us that life itself helps shape the limits of destruction. Short-term climate variability adds yet another layer of complexity. The El Niño Southern Oscillation ENSO alters both the strength and distribution of hurricanes from year to year. In earlier, more stable climatic eras, warm oceans may have supported repeated storms striking the same regions, leaving behind thick deposits that now testify to their violence. Today's climate, destabilized by both natural and human-driven change, produces greater atmospheric turbulence, which can restrain the size and intensity of any single storm. Historical modeling suggests that while modern hurricanes remain devastating, the odds of a storm reaching the gargantuan proportions of ancient superhurricanes are slim. Shifts in ocean temperature, atmospheric stability, and continental layout now impose natural limits on storm growth. Yet, with 21st century ocean warming, scientists warn that the planet may again be edging toward conditions that once fueled those prehistoric giants. In the end, the geological story of hurricanes reveals a larger truth. The storms we face today are part of a much older, grander pattern. Their power, structure, and movement reflect the ongoing dialogue between sea, sky, land, and life. And through that dialogue, Earth reminds us that even the fiercest tempests are but moments in the planet's deep, restless rhythm. Hurricanes, both modern and ancient, have long shaped the fate of terrestrial and coastal ecosystems. Their power extends far beyond the immediate destruction of human infrastructure. These storms sculpt landscapes, redistribute sediments, and influence the course of biological evolution across millennia. In the distant past, when superhurricanes larger and more intense than any seen today swept across tropical oceans, their effects reached hundreds of miles inland. Floods, ferocious winds, and massive storm surges reshaped rivers, deltas, and shorelines, displacing sand, silt, and organic debris. Over time, these forces created intricate geological formations, records that scientists now read in sediment cores and rock layers. The long-term impact of hurricanes on coastal forests has been equally profound. Falling trees, toppled by violent winds, opened clearings that allowed new plant species to thrive. Dead wood and leaves decomposed under the work of fungi, insects, and microorganisms, enriching the soil with fresh minerals. In regions where hurricanes struck regularly, forests evolved greater wind resistance. Trees grew shorter, more dispersed, and more flexible, better equipped to endure future storms. This illustrates how hurricanes, though catastrophic in the short term, have acted as evolutionary forces, driving adaptation and renewal across centuries and even millennia. Hurricanes have also been architects of marine and coastal ecosystems. Coral reefs, lagoons, and estuaries have long endured the battering of storm-driven waves and abrupt changes in salinity. While some reefs were destroyed, hurricanes also fragmented coral structures, scattering pieces that later settled and seeded new colonies. In river deltas, hurricanes deposited organic and mineral sediments, altering river courses and creating wetlands that became sanctuaries for birds, fish, and small mammals. Geological evidence shows that Pleistocene and early Holocene superhurricanes could move vast masses of sand and sediment dozens of miles inland, sculpting deltas and beaches in ways seen today only in ancient stratigraphic records. Repeated hurricanes laid down distinct sedimentary layers that allow scientists to reconstruct both the intensity and frequency of prehistoric tropical cyclones. What appears to modern humans as natural catastrophe, to geologists stands as testimony to Earth's deep time processes of transformation. Hurricanes also influenced evolutionary dynamics. Trees that survived multiple storms passed on traits such as wind resistance, flexible trunks, and rapid leaf regeneration. Animal species adapted in turn. Birds sought sheltered nesting grounds. Fish migrated as salinity shifted in estuaries, and small mammals found refuge in fallen logs and burrows. Hurricanes thus served as agents of natural selection, subtle but persistent forces shaping the composition and resilience of ecosystems. Ultimately, the geological record of hurricanes reveals that nature operates through cycles of destruction and renewal. Each storm, though devastating, injected new energy into the ecosystem, reshaping landscapes, stimulating biodiversity, and accelerating geological and biological processes. In this sense, hurricanes have been not merely destructive tempests, but vital engines of planetary change, molding Earth and life itself for millions of years. Hurricanes, though often perceived solely as destructive weather events, play a fundamental role in shaping both terrestrial and marine ecosystems. Their powerful winds, torrential rains, and immense storm surges move vast quantities of water and sediment, yet also set in motion cycles of ecological renewal in regions repeatedly exposed to their force. On land, hurricanes can snap and uproot trees, destroy old shrubs, and flatten sections of forest, but in doing so, they create new habitats for pioneering plants, insects, birds, and small mammals. Fallen trees and organic debris provide food and shelter for countless organisms, fueling the natural process of ecosystem recovery. In tropical regions where hurricanes strike frequently, plants have evolved remarkable adaptations for life amid regular destruction. Many trees possess flexible trunks and branches that bend rather than break, while pioneer species are designed for rapid regrowth after a storm. Animals, too, have evolved survival strategies, migration patterns, sheltering behaviors, and breeding cycles timed to calmer seasons. As a result, hurricane-prone regions form intricate mosaics of habitats where ecological succession follows cyclical, self-regulating patterns. The marine impact of hurricanes is just as significant. Strong winds and waves churn the ocean's upper layers, bringing nutrient-rich waters from the depths to the surface and boosting plankton growth, the foundation of marine food webs. While coral reefs may suffer damage, hurricanes also clear away overgrown algae and weakened corals, creating space for new life to flourish. Coastal floods deposit mineral-rich sediments across deltas and estuaries, reshaping the seafloor and forming fresh habitats for fish, crustaceans, and waterbirds. In this way, hurricanes act as nature's ecosystem managers, balancing biological systems and stimulating biodiversity through disturbance and renewal. The long-term ecological effects of hurricanes include shifts in plant and animal succession. Certain tree species may temporarily dominate due to their rapid regrowth, while others colonize newly opened spaces. Wildlife adapts its feeding and nesting strategies to changing landscapes, creating dynamic ecological systems that remain unpredictable in detail, yet stable over decades. Hurricanes are also potent geochemical forces. They transport vast quantities of salt, minerals, and organic matter between land and sea, enriching coastal soils and altering nutrient balances in shallow waters. Over time, this flux of matter and energy reveals a deeper pattern, not chaos, but a natural rhythm that sustains life. In this light, hurricanes emerge as both creative and destructive powers, integral components of Earth's biosphere that drive adaptation, innovation, and ecological balance. As climate change accelerates, the ecological influence of hurricanes becomes even more complex. Rising ocean temperatures feed more intense, longer-lasting, and wider-reaching storms. These stronger hurricanes bring not only greater immediate destruction, but also deeper, longer-term ecological transformations. On tropical coasts, plants and animals are being forced to adapt faster than ever before. Pioneer trees recolonize damaged lands, birds and mammals alter their migration routes, and marine species adjust to shifting oxygen levels, temperatures, and nutrient flows. Climate change may also alter the frequency and geographic range of hurricanes. Regions once considered safe could begin facing major storms, driving ecosystems to adapt in unfamiliar environments. This creates new dynamics of ecological succession. Species that once lived apart now coexist or compete in novel, rapidly evolving habitats. Some interactions give rise to unexpected ecological partnerships, while others intensify competition for limited space and resources. In the oceans, stronger hurricanes stir deeper waters, temporarily boosting productivity, but potentially destabilizing coral reefs and sensitive marine habitats over the long term. Intensified storms reshape deltas and coastlines, accelerating erosion and saltwater intrusion, which in turn transform the composition of coastal flora and fauna. Hurricanes in the age of climate change thus represent both destruction and creation, forces that accelerate evolution and redefine ecosystems. Species with rapid adaptation strategies, pioneer trees, marsh plants, and marine organisms tolerant of wide environmental ranges gain an edge, while less flexible ones decline or vanish. Hurricanes in this sense, function as ecological selectors, hastening evolution and shaping the biological landscape at a pace previously unseen in natural history. On a landscape scale, hurricanes also forge connections between ecosystems. Coastal flooding can transport nutrients far inland, enriching freshwater systems and boosting productivity in distant wetlands and rivers. Conversely, the loss of mangrove forests or coral reefs alters local climates and hydrology, affecting both terrestrial and marine life nearby. Hurricanes thus serve as vital links in the planet's interconnected web of life, driving adaptation not only locally, but across continents and oceans. From a scientific perspective, climate change may lead to hurricanes that are more frequent, more intense, and more disruptive to fragile ecosystems. This reality challenges ecologists to develop strategies that embrace the dual nature of hurricanes, as agents of renewal and as threats intensified by global warming. In this way, hurricanes become not only meteorological events, but central forces shaping the future of the biosphere, demanding flexibility, cooperation, and resilience from all living systems.